Awesome, thanks. Well, it's official, folks. Looks like we can get started today. Our goal for this week, we're going to be working through sections 7.3, 7.4, and potentially section 7.5. But the good news about all that is we're most of the way through this section 7.3. 7.4, I feel like the heat cools down a lot. We're not looking into trigonometric functions, identities, and weird U substitution methods. It's more of an algebraic section, 7.4. There's a little bit of long division in there, but nothing too major. The big part is the partial fraction decomposition theorem. It takes a while to say. It looks like a pretty ugly looking theorem, but it's one of those things where you practice it how it goes a few times in the notes and the homework, and it does come together pretty well. Then section 7.5, it's going to be our big review section on integration. So that's where we kind of slow down the course a little bit before we get into the other topics like approximate integration, say Simpson's rule, midpoint rule, that kind of stuff. And then into improper integrals being, I'd say, the big capstone of this chapter. So we're on the third week, and what I hope to get done once we get done with the grading at the end of the week is I'm going to start to turn over to attention to this side of the Moodle website. I'll begin building out the definite coverage that you can expect on the third exam, as well as some strategy guides, review problems, that kind of stuff. And my goal for what should be on exam 1, exam 2, exam 3 is I'm trying to get to the point where I see where we end exactly on this week. Then anything we cover on this week, well, you'll have your ordinary homework assignments due 1 week away, but that content won't fall in exam 1 because I feel like the questions that make the most sense on exam 1 are the questions that you've solved, had a chance to work on as homework problems, have a chance to get back so you can see the feedback on those homework problems. So I'm going to cut exam 1 short of anything that we cover on this week here. It's going to end on what we get to on the end of this week. So that's the reason why I'm usually waiting till around here to see where we end up at. But that's where we're at so far, folks. Any questions at all, Ben, to get us started? Okay, well, let's see where we left off. In section 7.3, let's maybe just delete that for a moment. That is getting us started, but we'll get through that looking at it from scratch. Here we're dealing with integrating certain functions. These are not even rational functions due to the square root symbol here. They're functions where a U substitution might not make any sense at all, or it might use an extreme amount of ingenuity to get through. And the idea is these are the expressions that we're on the lookout for to use trigonometric substitution. The moment we see a square root with a variable x squared minus a constant, it suggests that we should be on this part of the table. But notice our format isn't perfect, right? This says use x equals a secant theta. The a comes from taking the square root of the constant term right here. We have something extra. We have a coefficient right above. There's a couple strategies here that you could take. One strategy is you can force this symbol to look like this by taking square root of 9x squared minus 4. You can factor out the square root of 9 to leave x squared minus 4/3. So the whole result would be 3 root x squared minus 4. Oh, that's a 4/9 if you factor out 9. Let me try again on that one. So if you went that route, you have a third out in front of your integral, no big deal. But now this fits the format of what you're looking at right here. But there's two strategies now. Another strategy is to do this. Go x equals, we know it's a secant. The value of a is informed by whatever this 4 is. We take its square root, put a 2 down below. And if there's a number in front, we take the square root of that one as well, but it goes into the denominator. A little bit harder to see how that should come together by the red dot. But if you did the scratch work over here, I think it's conveyed a little bit better. You're taking the square root of the entire 4/9, and it just turns into this, 2/3. So I'd say pick the path that makes the most sense. But when you get started on this technique, you find out really fast if this is the right thing to substitute. So there's a great error check right in the first couple steps of this process. So x will be 2/3 secant theta in this problem, and then we'll go from there. Any questions picking the value for x here? Okay, and for a pretty legitimate step-by-step process, you could say, in starting these problems, you would always want to do this right out of the way. For sure, I mean, it's a substitution problem. You've got to say where it is. This part is actually easy to miss, though. The moment you have x, you should immediately go and calculate dx. That way we don't forget to throw it into the problem because it's replacing this part, completely replacing it. So dx is just a differential of the equation on the left here by the red dot. We'll get 2/3. Derivative of a secant is secant theta, tangent theta, and then we include d theta to make it a proper differential. I sometimes forget that, but I always try to put it in. Let me know if I forget my d thetas or dx's and such. After we've got that down, we now want to know, can we really simplify that given the substitution we indicated? So I would think of this as a good step 3. In step 3, we're going to the region of the integrand, which made you want to do a trigonometric substitution in the first place, and just simplify that down. I usually simplify on the right here so that I'm not copying the whole integral line by line. That's a lot of extra writing, but no harm if you prefer to just visualize it that way. So separating it out, I've got root 9x squared minus 4, turning into the root of 9. We're squaring this x here, so this is going to turn into times 4/9 secant squared theta minus 4. So now a third way to think about why is the 3 in the denominator, it's the only number you could throw in there so that when you square x, you get a 9 right here, which is going to cancel with the 9 we'd rather not deal with in the first place. So it's just gone by this step. So that cancellation happens. Now there's a 4 here and here, which means we can factor out root 4, leaving behind secant squared theta minus 1. And then the identity comes into play. The secant squared theta minus 1 now tells us we're dealing with the tangent squared. So this turns into 2 root tangent squared theta. And then when we think about this domain right here for the variable theta, its whole purpose is so that tangent itself is positive, and you take the root of the squared portion, absolute values will fall off. So finally, all said and done, this becomes 2 tangent theta. We'll highlight that in yellow to say that's dropping into that location. Now in step 4, we put it all together. So if you think about how we've been doing just about every integral from day 1 of this class, it all kind of goes like this. We do the operations on the right, that's going to convey the substitutions, the differentials, or whatever extra algebraic bits we need, maybe changing limits of integration. Then when we do all that organization, we come back over here and we just put it all together. It is a lot of organization, but if you get into the habit of organizing your work, not necessarily this organization, just whatever makes sense to you, its purpose is to make this content more robust when you go to do this problem on a final exam. You want to have a procedure that you're just used to flowing out every single time you do the problem. That way the problem won't feel like you're drawing a blank when you're looking at it. You'll have a definite way to get started. So next thing we do is, again, put it all together. Yeah, question first. Yeah, so that 4 is a really tricky one right there. Thanks for mentioning it. We've mentioned it before, but we've never really fully explained it. When it comes to square roots, you have a property that goes like this. Root times a and b becomes the root of a times the root of b. That's a fantastic property. It works for division. It does not work for addition. So don't even try if there's a plus in the middle. You have to do the order of operations first. Exactly. So we used a different process on this one. Using this formula up here, we took root, let's call it 4x minus 4, just to make it an easier problem to look at. Essentially just this right here, with that 4 in blue and that 4 in black. We could call this root 4 times x minus 1. And now the 4 is playing the role of A, the x minus 1 is really playing the role of B, and it now factors in this way. Root 4 times root x minus 1. So it's just a weird kind of trickery with these factors, A and B. And the fact that 4 square roots you can split across multiplication in that sort of way. Does that make sense, seeing it that way? Awesome. And again, that's important because the only reason we picked out that 9 is to clear it out, leaving just 4s right here and here for that property on that line. Other questions at the moment, seeing how that root 4 went? Okay, so next thing we can do is here, on step 4, putting this all together, we have integral of 1 over the root 9x squared minus 4. Following the color coding, we're just putting in a good old 2 tan theta. Next, for dx, I like to put a times here to say we're using the differential next. It's all of that. The 2/3 secant theta tangent theta d theta gets dropped in. So now 2/3 secant theta tangent theta d theta. And I'll just put a quick border here. At this stage, we're just focused on finding out what this integral is going to look at like. Then we'll have to do the tricky steps in step 5 of undoing the step here, that substitution. But first, let's make this a little bit easier to work with. We can simplify and call this, well, the 2's cancel. That's already a big deal. The less stuff you're looking at inside your integrand, the better. Let's pull out the 1/3, keeping that thought in spirit. Next, tangents cancel. All we want then is the antiderivative of secant theta d theta. That's a tricky antiderivative. We derived it, but the derivation doesn't necessarily help us remember what it is. It just helps us rederive it. Anyone happen to recall what that would be? It starts with a natural logarithm of absolute value. Good call, absolutely. That's how we pretty much try to remember it. If you're integrating tangent, cotangent, secant, and cosecant, all of them start with natural log absolute value of something. And when it comes to a secant, it's secant theta plus tangent theta plus a constant. If this was a cosecant theta, actually, let's just write that up above. For when this one comes up, cosecant theta, it will become just like this, natural log, absolute value, cosecant theta, one small change, put a minus there. So we have the co-function, we have the small change, the minus that came into play, then go to the next co-function, tangent to cotangent, plus a constant, and that's a formula for whenever cosecant theta comes up. So this is looking good, but there's a significant amount of credit for the 5th step, undoing our substitution. I guess 6 steps, depending on how you call them. Let's call this step 5 next. In step 5, we return to this statement. Our objective is to solve for the secant theta function. So secant theta turns into multiply by 3, divide by 2, so 3x over 2. If you were a fan of SOHCAHTOA from last class, then this is a good time to draw it in. SOHCAHTOA, so there it is. And here's how I would use SOHCAHTOA in this situation. We're dealing with the secant, which is reciprocal to the cosine function, so we're at the CAH part of SOHCAHTOA. Because it's a reciprocal, it goes backwards. Hypotenuse first in the numerator. So I'll write HYP for the H. A next for the denominator, the adjacent side. Next, we can just draw in our right triangle. But notice right here, we've already have secant theta. It's 3x over 2, so that's half our substitution done. That's kind of nice. We can get tangent theta, we're on our way. So I'll throw theta there just because it's a convenient spot. Here's the right angle. And back to this, when we said 3x corresponds to the numerator for hypotenuse, it meant we were writing 3x above here. For 2 being the adjacent side to theta, that means it would be this side here. This side would be the opposite side, for example. And you know what? Doesn't hurt to write that in. Let's write that in, just for the sake of it. This is the hypotenuse. And this is the adjacent side. Adjacent to where you place theta. This is the opposite side. Opposite to where you place theta once again. And my claim of claims here is that the opposite side should be the square root of 9x squared minus 4, which came from the original integrand, that denominator there. You always want to double check that because this would be another internal check in the process. If we've done everything right to this stage, well, as far as the substitution is concerned, we should be able to take the square of this side, set it equal to the square of this side, set it equal to the square of the square root on this side. I don't always do this check, but it's worthy to do a couple times, especially if you're trying the right triangle procedure for the very first times to seeing if it works. So on the left, it's 9x squared equals 4 plus 9x squared minus 4. What happens with the square root and the power 2 is they annihilate each other. And then down here, yeah, 9x squared would be equal to 9x squared. So that tells us, here's our check, we're on our way with this. And all we need to do is say what is tangent theta per this diagram. So here's how our final answer comes to be. It's 1/3 natural log. In place of this secant theta, we can just drop in 3x over 2. Then plus, for tangent theta, you can use the SOHCAHTOA method once again. Tangent is the opposite side divided by the adjacent side is what it conveys. Opposite side is this portion, root 9x squared minus 4. Keeping them in the color coding just to show where they came from. Divide by the adjacent side to theta, that's the 2. Now we can close absolute value, add the constant, and this is the final step. Step 6 here is to finalize undoing the substitution through step 5, either building a right triangle diagram or doing something else. Usually, this is just the fastest way to put the information together, get your secant and tangent out. So I usually just go that route. We did it, folks. This is a pretty not great looking antiderivative to take on, but these are the kind of problems that we'll practice quite a bit in the homework. Exam problems are not going to exceed these kind of problems you see here on complexity. They're going to be very similar to what you're doing in the homework problems as well. Well, any last questions, folks, on getting through this one before we try the next? Oh, I gotcha. So for that one, let's write that out. Oh, I was thinking about the diagram here, right here, but you could also think it should be equal to this as well. So when we came from here, we multiplied by the 3, divide by 2. And this portion here just turned into that by solving. Then because just secant theta came in, we just dropped in the value. But another way to think about it is, let's suppose we were to this line. All we had is the triangle. We should be able to build out that secant theta. Secant theta should be through SOHCAHTOA. Going over here should be the hypotenuse first, reciprocal of cosine, divide by the adjacent side. So it would be the 3x hypotenuse, divide by the adjacent side, which is 2. So again, doing it this way, even though that was there, not a bad idea because it's another check. Did the diagram even make sense when we built it? This SOHCAHTOA stuff, especially with the secant function, which flips the order of the fraction, is easy to lose track of until you practice it a whole bunch. So that's a good double check as well. Other questions so far? Okay, well, we did it, folks. That's our first problem of the day. It's amazing that these problems take just about 10 minutes to get through, but that's a little bit more like 20 minutes to get through. But we're practicing it as well, so they don't take as much time once we get some good practice. However, this one is actually a hard one. I have to be pretty honest. Some of the problems that I do assign in the homework are just a little bit harder than normal. If I feel like that's what happens, I always try to put this down on the homework sets. For example, exercise 19, I mentioned benefits from a very specific double angle identity. That's because when you go to integrate, you're going to use a reduction formula, which involves a 2 theta coming in, but your right triangle is involving just theta. So you actually need this formula right here to break it down. And this is a problem where just something like that's going to come up. There's some nasty identity here that we need, and we can either derive it or use a shortcut. I'll leave it up to the class. Really, the first thing we have to discover about this problem is, what is the substitution? Anyone spot what it should be? Good call. From class, we've got a suggestion of going tangent theta, and that's exactly it, because the coefficient 1 right here means using this process, it'd be 1 times tangent theta, so just a tangent theta. So it's kind of nice in a certain way. This problem gets going pretty quick, right? So we don't have any weird things to worry about with the constants like in the last one. We'll come from here and immediately calculate dx. That's going to be a secant squared theta, d theta, and that fully replaces this part. I guess the substitution tangent theta replaces that denominator. And just like before, we're re-expressing root 1 plus x squared. So this will turn into square root 1 plus tangent squared theta. So now it's the square root of, by this identity in row 2, secant squared theta. And we get just an ordinary secant theta out of this thing. So back over here, once we have all those 3 moving parts, we just jump it all back into the integral. So same kind of substitution business as normal. Any questions on this worker through here to the right? Okay, dropping this all in, root 1 plus x squared we found to be secant theta in this problem. Denominator is our substitution. X goes to tangent theta. Using the differential, that bullet is just my personal way of organizing. The differential's coming in. We drop in secant squared theta d theta, which means what we're integrating is secant cubed theta divided by tangent theta d theta. And this is at the point at which I think this becomes out of nowhere a pretty hard problem. I decided to keep it in the notes because it's a good way to think about trigonometric identities. And I do have a cheat sheet on this one. This is the part I'll leave up to the class. If this was a problem that came in as an actual homework problem, I would definitely put down something like this. Hint, I've got an identity here that says secant cubed theta tangent theta, nope, secant cubed theta divided by tangent theta. My claim is that that is somehow, some way, a secant theta tangent theta plus cosecant theta. But I'll leave this up to the class. Should we check it or use it? Any volunteers for deriving that identity? Or would you rather insert it into the problem and go from there? Takes you back to trig, right? You'd be proving that this is a trigonometric identity by starting on one side, doing a bunch of algebra, and hoping it turns into the other side. The left side is our integrand, But what's special about the right-hand side is, if it really is a trigonometric identity, antiderivative of the first term is secant. Antiderivative of the second term, well, we discussed that one. That's the one that goes natural log cosecant minus cotangent, close the absolute value bars around those. But deriving this one is kind of painful. So if you're not too sure on this one, I totally understand. My trick was I made this a secant cubed times a cotangent. Then after that, I expressed everything in terms of sines and cosines, started canceling. I found use of these identities along the way to get everything just right. And let's go with the route of just applying it here. Let me know if you would like to see the identity solved. We can give it a try later. But it now turns into, by the hint, antiderivative, secant theta, tangent theta, plus cosecant theta. From here, the problem is now much, much more approachable. So watch out for things that somehow just don't seem like they're working out very well in the homework. This is one of those examples. If there is no hint, but first check to see if there is one, don't hesitate to reach out. It could be something weird where I just forgot to put in a hint. The problem was harder than it was intended to be. But for this one, we've got a ready-made antiderivative. Secant theta tangent theta has antiderivative secant theta. This is the tricky one. It goes plus natural log absolute value cosecant theta minus cotangent theta plus a constant. So we've got it, folks. This is the antiderivative. Then we just have a major problem with our work, right? Every substitution has to take us back to the variable indicated right here by the red dot. If it says dx, we have to return to x, but it's not straightforward because we have to deal with these functions right here to make that happen. We need to know how secant theta relates to tangent theta, in other words. That's tricky if all you're using is trigonometric identities, but that's why we go and just throw down our right triangle. It's really fast to just convey all the information almost instantly. So start here. Well, maybe if you prefer, you could start with this. So TOA. Then next, tangent theta is equal to x, but you can always promote that to a full-on fraction. So that now using the SOHCAHTOA part, we can identify the numerator with opposite of theta, the denominator with adjacent theta. So next, here's our right triangle. Okay, so we've got theta, and let me put in those descriptions. Longest side is always the hypotenuse, and adjacent was always a weird word for me when I was learning right triangle trigonometry. Opposite makes most sense. So this side is opposite, side furthest away from theta, and that just leaves adjacent side. It's the opposite of opposite in the sense that it's the side that's touching. But that didn't make sense to me either because so is the hypotenuse. That's the longest touching side. So now, opposite is x. Adjacent is 1. And if you use Pythagorean's theorem here, we take 1 squared plus x squared and square root it. That would be 1 plus x squared. Let's highlight that in yellow because as a check, that has to be something from your integrand or else there's a problem in our right triangle. So that tells us we're on our right way, and now we can finalize the rest of these computations. Let me fix that first. Well, any last questions, folks, before we finalize the substitution undone? Okay, let's give this a try. First, in place of secant theta, well, secant, coming back from this, should be hypotenuse divided by adjacent. So take the cosine information and reverse it. Hypotenuse is this, root 1 plus x squared. We're dividing by the adjacent side, which is 1, so we can just leave it off, make our answer more simplified by leaving it in this format. There'll be plus natural log absolute value. Well, let's not. I was thinking about keeping that yellow, but it'll start to get too overwhelming if everything's highlighted, so I'll leave that one off here. For cosecant theta, any volunteers for what that one should be? Turns out it's not one on this one. Good call. So the way you can think about it through SOHCAHTOA is cosecant is the reciprocal of the sine function. Reciprocal means you just read these going backwards. H first for hypotenuse, like you said, root 1 plus x squared. Once I grab the pen tool, there we go. Then you go to O, the opposite side, which was division by x. Then one more to go. Hang on, let me make that a real x. The last one's the cotangent function. And we don't have to think too hard about cotangent. Because if you have tangent on paper right here, cotangent's just the literal reciprocal of that. Go 1 over x, and you've got it. Add the constant c. And so far, that's our antiderivative. Looks like it'd be a complicated one to check. You'd have multiple chain rules going on here, interesting derivatives. But if you differentiate all that and simplified extremely carefully, you should get back up to the top. The weird thing about these problems, though, that I often mention is the calculus going in this direction, finding the antiderivative through trigonometric substitution, is easier than differentiating these kinds of answers sometimes. That's a lot of work to differentiate. Yeah, go ahead.
I don't know if it was coincidental or if it's something that will happen, but on this one and the last problem, everything inside the natural log shared a denominator. Is that something that would just happen, or was it just coincidence on the thinking that it was like that at the end?
I think it's a little bit of both, if that makes sense. That's a weird answer, but I think the commonality had to do with the fact that we were dealing with a tangent function on both of them. So is tangent here? Oh, hang on. No, that is not the commonality. Yeah, that might be an interesting coincidence then. So looking at even a prior one, we have maybe a little bit of variation on this version. We had the x going down below. And on this one, didn't actually convey in the same way because it was a definite integral. But yeah, that's a good, interesting observation. I don't think it happens on all problems based on the ones I've seen in the homework. But what more to say about it? I would say another thing to think about is one reason why the x's were in the denominator, maybe it was more to do with the cofunctions coming up more than anything. Because if a cofunction comes up, you're throwing your hypotenuse up into the numerator and leaving these factors down below. And back up here, we had a cofunction. Oh, nope, the pattern broke on that one. That one was actually a tangent. Looks like it was more of a coincidence on this one, potentially. Could require further investigation. But other questions so far or observations? Okay, at this point, we pretty much did it, folks. This gets you through all the main questions that you're going to look at in the trigonometric substitution section. So I have one more question, but just like on the other sections, this one is just a way to review multiple techniques all in one. So let's go this one alone, no table to help us out. And we want the antiderivative of one big mess like this. Already what might be bugging you is the dy. I put it here since the author does it occasionally. But if that bugs you, you can always think of it in this kind of way. Those would be algebraically equivalent integrants, either way we look at it. So let's leave it this way, just for a way to emphasize you can change the way you format your problems, even if the book has it formatted differently. In this problem, probably a u substitution is a good start with it, right? It's really complicated with the y here, a natural log y squared. The most inner function I see here is this one. It's inside the squaring function, which is inside the 1 plus something squared function, which is inside the square root function. So there's lots of compositions here. But we can let u just be natural log y. If it works out with the differential, then that's an automatic reduction in complexity for this big definite integral we're seeing here. Du then becomes 1 over y dy. The 1 over y dy are those elements there. It just kind of smattered all over the place, but it all is going to turn into du. This is going to turn into root 1 plus u squared. The one thing we do have to worry about is changing limits of integration. If we don't change the limits of integration, and trigonometric substitution comes up, then you have to do all of this work in the middle of the problem. Again, it is a lot of effort to do that. So that's one of the ways changing the limits of integration is a big help in these longer problems, especially. So the variable was y. We should say y goes from 1 to e, the lower limit to the upper limit. So that same format, because we're pulling it out in that format. When we move to the right, here's the next tricky thing about this. Hang on. No, it's not too tricky. It's going to go right inside here, so it's natural log e. But let me say it this way. U is going to become natural log e. Down below, u becomes natural log of 1. And these become just fast values that come up a lot on these kinds of problems. Any logarithm to 1 is a 0. How about this one? Anyone spot the value for natural log of e? Good call. This one is exactly 1. So that's nice. We've got new limits of integration. Let's put this all together. It's now a definite integral from 0 to 1. So just a little highlighting here to convey what in the world happened to our limits of integration. The 1 over y dy all turns into du. Below we have square root 1 plus u squared. Oh, I still need a numerator. So there's our new integrand. We could put a little border here to say we're done with the u substitution method on this first attack. And it was worth it, right? The original integral is very complicated to look at. That's a huge reduction of complexity. We just had to change out a variable. But now that we're there, turns into a trigonometric substitution. One way to memorize the trig substitutions is anytime there's just a plus, that's an automatic tangent. If it goes 1 minus x squared, that's the sine. X squared minus 1 is the cosecant. But this one is the tangent for the plus. So we'll write u equals tangent theta. U, because that's the variable in the integrand so far. Usually this is an x, so we write x as tangent theta. Next thing we calculate is du. This is already right here. But we go right here to recalculate it and find a new expression. So tangent theta at u equals tangent theta, it turns into du is secant squared theta d theta. So that all goes into this position. Then next for the root, 1 plus u squared turns into the root of 1 plus tangent squared theta, which turns into the root of secant squared theta by our usual table. So that's just an ordinary secant theta right here in that denominator. But again, there's more drama going on with this problem. This is similar to the very first problem that we solved in these notes, where we're doing a trig substitution along with the definite integral means it's again a good call to change the limits of integration one more time. So let's do it here. The variable we're working on is a variable u. So we'll say u goes from 0 up to 1. Now, here's the portion that I was mentioning is a little bit different now that we're really doing trig sub. We're placing u right here where the red dot is. So we are getting an equation. 1 equals tangent theta. Next equation is 0 equals tangent theta. And our objective, because we're putting that theta into the integral, is to have a lower limit of theta and an upper limit of theta. But both of those are solved now through trigonometric equations because we have to undo the substitution. Even if we undid the substitution in this way, we still have to do some trigonometric evaluation in a way. So this again streamlines the process. It does cut down a lot on the work. But we do have to solve the equations next. So think of tangent theta as sine theta divided by cosine theta. We know sine of 0 is 0. And so that tells us the only way this equation is true is, well, not the only way, but the way for a value of the variable theta to be in the domain that we've indicated for trig sub is for theta to be 0 here. Likewise, anyone spot the value for theta up above to get tangent of that theta equaling 1? It wouldn't be 1. It'd be pi over 4. Good call. Absolutely. Reason for that is pi over 4 is a pretty special value on the trigonometric unit circle. At the angle pi over 4, here it is drawn in, your x coordinate becomes root 2 over 2, and your y coordinate becomes root 2 over 2 as well. So that means tangent pi over 4 becomes the sine value, the second coordinate right here on the y-axis, root 2 over 2, divide by the first coordinate, that value on the x-axis, root 2 over 2, because it does give us the one that we're expecting. This says pi over 4 does check on this problem here. So all of that is to say, we're integrating from 0 up to pi over 4. Well, any questions, folks, with those change? Let me undo this yellow highlighting. There's too much yellow on these notes, I think. So we started from 1 to e, but because we did a u substitution, we're going from 0 to 1. But now, because we're doing a trig substitution, we're going from really 0 to pi over 4. But this means we don't have to do 2 layers of undoing a substitution, one of which is technical because it's a trig sub. We're just going to take 1 over root 1 plus u squared, follow our nose down to this on the margin is a secant theta, times, from this portion du, go to where your substitution was, it's now secant squared theta, d theta, and after simplifying, we're only integrating from 0 to pi over 4, the function secant theta. So the integral on the top was just the world's most convoluted, unnecessarily complicated way to say, integrate that. That's the real problem we really want to do. And we won't undo any substitutions. We have the right limits of integration as well. So this came up now kind of like the 3rd time in class. It was a secant, then we end to the antiderivative of the cosecant. For this one, it's natural log secant theta plus tangent theta, and no plus c for a constant because we're doing a definite integral. We must evaluate from 0 to pi over 4. Which means, like we mentioned on a different section, 7.2, this is now becoming just a glorified trigonometry review type of problem. Let's first do the limits. We have natural log absolute value, secant pi over 4, plus tangent pi over 4, minus natural log absolute value. Now we're using lower limit, so secant 0 plus tangent 0. So if we can do all 4 of these evaluations, we'll be on our way. You know, we've done most of them actually, now that we look at it. We mentioned before, let's say this on the margin, tangent of pi over 4 is 1. So let's say tangent pi over 4 is 1. I guess I've said that 2 different ways as well. We also said that what tangent of 0 is through this equation. Tangent of 0 would be equal to 0. Secant 0, that's not so bad, because secant of 0, once I format that a little bit better, is just the reciprocal of cosine 0. So if you know cosine 0, you're on your way. Anyone see what the value should be for this?
1.
It's 1, absolutely. 1s keep on coming up today, it seems like. Cosine of 0 is 1, and secant 0 is just 1 over cosine 0 for a 1 over 1. Let's see. Really the only thing that is going to be a little bit more is that one, secant pi over 4. So secant pi over 4, if we want to calculate this from first principles, is 1 over cosine pi over 4, which is 1 over, here's pi over 4 on the unit circle diagram. It evaluates to root 2 over 2, the x coordinate. And from here, you could do all sorts of surgery to that number. You could multiply by the reciprocal, call it 2 over root 2. And I'm completely fine with that as a number. You don't have to rationalize your denominators. But if you decided to, let's go ahead and do that. You would take 2 over root 2, multiply by the irrational number in the denominator. Really, we're multiplying by the number 1. Up above, we get 2 root 2. Down below, we get 2. So taking that extra work tells us, finally, after it's all said and done, secant pi over 4 is root 2. So coming back over here, we can finally drop in our values. So from secant pi over 4, it's a root 2, plus tangent pi over 4 is a 1. Then we have a minus. Natural log, here we have a 1 from secant 0. 0 on that one. And we're just about there, but now more stuff happens. Over here, if you left your absolute values in, no harm done. But I think most often than not, you would see the answer conveyed this way, root 2 plus 1. You could say we took the absolute value. It was positive, so no change. That's the natural logarithm of 1, which came up before. I don't want to scroll too far. But that's just a 0 we're looking at. Absolute value of 1 plus 0 is just natural log 1. So we could go minus 0 just to emphasize we didn't forget to copy it down. And this is our exact answer to the question, what is the area under the curve generated by that function up above? If you ever need to know the answer to that question, it's that value there. Well, we did it, folks. That's dealing with a pretty nasty trig substitution with a u substitution in a definite integral. The main takeaway is it's just good to know how to track these substitutions and change your limits of integration, because I have tried this question without changing limits of integration. It takes like double the amount of work that you're seeing here on paper. It's a lot of work. It's easy to just miscopy or forget something as you're doing all that. But changing limits of integration, they're not easy either. It's a whole new process. If you're methodical like this, plugging things back in the exact order, it's not so bad. But it's a spot where you have to pay a little bit extra close, careful attention to, I'd say. Well, we did it, folks. That's the infamous section 7.3, trigonometric substitutions. It's rough because it's just a different way of doing a substitution. But once you practice it, it comes together pretty nicely. Any last questions at all before we go to our next section? Okay, so like I mentioned, I'd say as far as chapter 7 goes, this is one of the harder parts of chapter 7. It starts to cool off out for a while until we get to the last section, improper integrals. But for the moment, we're going to do something more relaxing. We're just dealing with integrating rational functions, which means the function is just a polynomial divided by a polynomial, literally. Here's what it looks like. Not that, it's coming. So my first part of these notes is one big exception. If we want to integrate this function, it has a problem. The degree of the denominator is smaller than the degree of the numerator. And that means our really fancy theorem that we're about to use, once I fix my windows, give me just a moment. There we go. This one, oh, that's not it. The partial fraction decomposition theorem doesn't work on this problem. Let's make a note right here, because that can cause a big problem in the homework if you try to use a partial fraction decomposition theorem here. Here, we must use long division. So that's one of the side effects if you're integrating a rational function. Long division could be part of the problem. And it's almost unfair, because if it looked like this, 3x squared minus 2 divided by x, that's a totally different kind of problem. Anyone spot the reason why that one out of nowhere does not lead to log division at all?
Coefficient. So like if it's the same power, you just take the coefficient of it, and there's like the numerator has a higher power, and the denominator has a higher power.
I think you're referring to, say, for example, if you're taking the limit, x goes to infinity, say 3x squared minus 2 divided by same power below. 4x squared plus 1. I like that you mentioned that because this idea actually comes back very, very big in chapter 11. So we're not going to leave these ideas alone. They're coming back. And the idea is, if you take a limit as value goes to infinity, you're just asking, what is the horizontal asymptote? Because it's a rational function, you can eyeball it. The degrees are equal above and below. It's just 3/4 on that one. So that's a nice little shortcut. We're going to use a lot in chapter 11 because we're going to do about hundreds of these different kinds of limits out of nowhere. But still in this question right here, it's fundamentally different from the one on the left. Anyone spot the difference? Yeah, go ahead.
Or you can simplify that one, you'll get the like integral of 3x minus 2 over x, and then you can integrate that separately, and that goes really.
Exactly, yeah. So the whole problem with this one, the reason this one's in calculus 2, but this one's in calculus 1, is because addition and subtraction often messes things up in algebra, and that's the problem right here. You can't split this integral, aside from splitting it up by using long division. Whereas over here, if it's a single term in your denominator, you have an automatic way to split it up, like you said. This turns into integrate 3x squared divided by x. That's just a 3x minus 2 divided by x. All right, is 2 times 1 over x. Only because that reminds me that there's a logarithm hiding right there. We get 3/2 x squared minus 2 natural log absolute value of x plus a constant, and then it's done. But over here, again, we have a big problem. It's a good idea to move backwards and think about the definition. In the definition, we're looking at a rational function. These are things we're integrating. Rational just means ratio. So it's a ratio of two things. We could call it r of x by q of x. They're both polynomials. And just like division by zero is disallowed, q is not the zero polynomial. You just have to say that somewhere. Yeah, go ahead.
Could you do division by polynomials to simplify it? Like divide it as a polynomial?
This one right here? Yeah, that's what we're going to do by saying long division. We'll be really doing polynomial long division right here. In fact, let's say that right here just to be specific. We'll use the strategy of not ordinary long division, but it gets more exciting, polynomial long division.
Oh, that's it.
Synthetic division? I do, yeah. I do, yeah. I can do it the synthetic way and the original long division way. So I'm happy to look at both methods as we go through this problem. I'll probably start with the normal long division way since I think most people kind of anchor to that process. Then I'll show it the synthetic way for those curious. Other questions at the moment? Okay, so a rational function has to look like this, r of x divided by q of x. And then the moment we say that, we're really concerned about the degree. Numerator of this rational function has degree 3, just because of that part right there. It's the highest degree term that existed in that numerator. Q of x has degree 2 because of this position. And suddenly, this is the big remark that we should watch out for. Not because it comes up all the time in the homework. You'll probably have to do this 2 or 3 times. But you don't want to have a trick question those 2 or 3 times it comes up. If the degree of the numerator is greater than that of the denominator, like in that configuration, we need long division. Unless it's this, just keep on doing what you would typically do in this situation. So what do we do if this is reversed? Suppose this was not an x plus 1, the denominator. Let's say it was x cubed. Long division's off the table. We can use something else to integrate this. So when it starts to look like that, where the numerator does not win, when it doesn't have greater degree, we're going to use the good old partial fraction decomposition theorem. Like this is formatted a little bit weird. There we go. The partial fraction decomposition theorem has 4 different parts. So it feels oppressive the first time you look at it, especially because it's a lot of reading. So part of my job is, once we look at this in more detail on Wednesday, is to convince you it's not that bad. It's going to be a hard sell, but when you do the homework problem, it'll be very similar to example 2. You just don't have this stuff in the middle. You're just going to be re-expressing these using the theorem without solving for the coefficients. I think you have 4 problems like that in the new homework set for this section. Once you get through all that, Sure, it's a long to state theorem, but when you see how it works by doing those examples, it's not so bad. I promise you, it looks a lot worse than it seems. Then on example 3, we'll actually integrate them. We'll do the top-down process, apply the theorem, solve the coefficients, substitute them back, and integrate whatever we have. So it's a long process. We'll be probably finishing these notes on Thursday's class. But for today, we end at 8:37. I think we have just enough time for a long division. How about we end on this one today? Does that sound all right? Okay, first, I'm going to do the long division way, and then the other method, the box method, as you refer to, also called sometimes synthetic division. For the long division approach, the idea is we're taking this whole thing, take the divisor x plus 1, divide it into this portion, 3x squared minus 2. I think we call that the dividend. Not that it's super important. I just think those weird words are weird. 3x squared. Good idea to put in plus 0x as a placeholder. We'll use that in synthetic division as well. Minus 2. The thing that goes into the numerator is going to be our quotient. And we start off by doing the following. I'm going to use some temporary highlighting to indicate what we're really doing. We focus on the term with the highest degree in the divisor, go inside here, and just divide it into this. So when this x divides into 3x squared, we get 3x. Where you write it down isn't super important for polynomial long division, so I usually just move it slightly to the right. That's just my formatting. If you put it clear over to the left, no harm done. Now, next step, once you have this 3x, you take this whole thing and distribute it back into your quotient, your divisor, x plus 1. So just imagine a distributive law. 3x by x gives you 3x squared. We're expecting a match here. Any difference tells us we made a mistake. Then multiply it here to get plus 3x. And that stage is done. We come down here, and now we multiply this whole thing, bottom row, by -1. We're doing polynomial subtraction now, just on column 1 and column 2. So one way to convey this is, some people like to go like this. Visualize the negative sign being distributed through. I think that's a great way to visualize it. For me, though, it tricks my eyes when I see it that way, so I usually write it out this way, just to be extremely specific. -3x squared, -3x, and I would circle my negative sign to remind me that's the sign I'm really using. But pick the way that makes the most sense to you. The parenthesis way is a very descriptive way as well, and it's less ugly. You're not writing things over. We get a 0 when we actually tally this up. By design, that has to be 0. Over here, it's 0x minus 3x. And now we're in the rinse and repeat part. Carry down the next term, -2, and divide again. Anyone see what should go up above? Good call. We'll get the -3 because we're taking this x, dividing into that whole term right there, that -3x. So -3, like you said. After you get that -3, take the -3, so the sign included, distribute it through x plus 1, and we get to -3x minus 3. So that part's done. Finally, we're going to change the signs. So come over here, I'm multiplying everything by -1, flips to positive and positive. In this location, when I have a negative sign, I just put a vertical slash to say, now I'm doing positive. We get 0 by design. Here it's -2 plus 3, so a positive 1. And that's our remainder. The big strategy now, once you have all this, is to put it all together and say, you are now integrating. Put in, this can benefit from some color coding. Put in this part, 3x minus 3. I notice we're doing really great so far because those are terms that are very readily integrable. But there's one last term. It's generated from the remainder. That remainder 1 right here is still being divided by the divisor, x plus 1. So we go plus 1 over x plus 1. So by using long division, this is what we're integrating now. It's our best technique of taking what we did on orange, the problem we'd rather do, where long division is not required and we split up terms. If we can't do that because there's more than one term in the denominator, this is our next approach. And we're just about there. Let's integrate this, and then we'll look at this division from a different side. So antiderivative of 3x is just 3 halves x squared. Antiderivative of negative 3 is just a minus 3x. This one's tricky though, but there's a hint. Antiderivative of 1 over x is the natural log of absolute value of x. And same thought here. This turns into the natural log, absolute value, x plus 1 plus a constant. And the reason that part works is you differentiate the natural logarithm of x plus 1. Let's do it down here in the margin. A couple of pretty amazing things happen. The first thing is that even if there's an absolute value inside your logarithm function, the x plus 1 still comes down into the denominator without absolute values. It's kind of amazing in a way. Then you multiply by the derivative of what x plus 1 is, but that's just a 1. So we get 1 over x plus 1 as expected. That means that's really our antiderivative down here. I feel like I should box this answer out because my work is kind of all over the place. So that's all we have to do on this question. But what makes this question hard is you have to spot the reason we did long division. Numerator is of higher degree, is the only reason. Well, any last questions, folks, for getting through example 1? Okay, and then as promised, not everybody's a fan of long division as done this way. Pretty much every time I do long division like that in class, there's a question about synthetic division or the box method. So let's give it a try. And it's a very good method, I should mention. It's in the spirit of what a lot of mathematics is all about. If you have taken linear algebra or you're about to take linear algebra, the theme there is it's all about the coefficients. Same thing in synthetic division. That looks impressive, but doing this division has not as much to do with all the things we wrote down. It's about the numbers, the negative 3s, the positive 3s, the negative 2s, the 1s. If you can track what happens to the numbers, then you're doing division either way. So here's how it starts. 3x squared minus 2 divided by x plus 1. We focus on the plus 1, and we box it out. Change its sign to now a negative 1, and then come up to the numerator. We're pulling coefficients. It's going to be the coefficients we see over here. So it'll go 3 for the x squared, 0 for the x term, negative 2 for the constant term. Exactly what we put down in this portion right here through traditional long division. Then we drop a line. Here's where it gets a little bit interesting. We start this off by just carrying 3 down. So there's 3. Next thing we do is a multiplication. This part multiplies whatever you have here. So don't forget to change the sign. If that was a minus 1, I would have had plus 1 right here. When we multiply, that turns into a negative 3. And then we take a tally. 0 minus 3 drops down to a new value of negative 3. But notice so far how similar this all is. We got a 3 to start. We took a 3 minus 3 for a 0, a 0 minus a negative 3, and same as here as well. So the method down below is just a way to do all of this, but not copy down x squared, and so on. Next thing we do is we take the negative 1, multiply way out here now, so now it's a positive 3. Once we get those results, we scoot them kitty corner to the right in that way. Now it's negative 2 plus 3 for a positive 1, matching up what we had right here. Then we take these components, positive 3, negative 3, positive 1, and let me rewrite this, 3x minus 3. And then we just drop them back. If you were at 3x squared and you got those coefficients, those are coefficients for 3x minus 3 plus 1. So we're pretty much just reading this all out. but that plus one is also going to be divided by the x plus one in that way. So that's how you take the results of this very different looking numerical game, which is just this without as much noise, and you convey it back here. Here's the positive 3 coming from this. X is now power 1, negative 3, and the remainder through synthetic division goes here, but you still have to divide by x plus 1 either way. Well, any last questions, folks, on either the division side or the integration side?
The negative one came from the denominator of b plus one. You just take the opposite of it.
Are you looking down here?
Yeah, for synthetic division, where did the first negative one in the box?
Oh, gotcha.
It's the denominator's opposite, right?
Yeah, exactly. And another way to kind of connect the dots here is, notice in long division, we were always subtracting each of our rows. If you put the negative 1 right there in that spot, that's the analogous thing. You're subtracting on your rows by putting that in opposite side. But yeah, that's absolutely right. Whatever is here, take your opposite. Other questions at the moment? Okay. Well, this feels like a good stopping point for us. I don't know how to end at 8:37. That's honestly some reason really, really hard. But if you have any questions, I'm here for just a few minutes. Otherwise, I'll see you all on next class on Wednesday. Hopefully I can use words a little bit better by then. Talking was hard today for some reason.
I don't know if you prefer to do it on a Word document.
Yeah, I'd be happy to. That could be pretty easy.
The review.
Let me pull up a fresh document so we're looking at something a little nicer. They seem to do that. Let me fix that. Okay, so what were you looking to review?
When given. Doing anti-derivatives for the integrals and start by just the second derivative, second or third derivative, or with that.
I think I have a problem I could pull up for something like that.
Like velocity, like.
Yeah.
Negative 18 velocity, and you have to work up to the
Acceleration.
the slope equation.
Well, let me see what I've got. I'm pretty sure that sounds familiar. And let's see here. It's fall 2023. Let's go with fall 2024. That would have been, oh, this isn't this is calculus 2 again. Let me try again. So calculus 2. I thought this was easy to find at one point. There they are, calculus 1. I don't know why that's so hard to find.
These ones I always struggled with on the exams for some reason. I never got them right. Because I could get, well, I get majority of the points, but I couldn't figure out the last part of them.
Gotcha. Oh, I want to go to this part. That would be chapter 5, I believe. Yeah. And I want to go to indefinite integrals.
Honestly, if I have. I even have the exact problem on Bill.
That could work too, yeah. This is the problem I had that I was referring to.
Yeah, it was along these lines. You have to like work backwards. You're given. I can't remember if it was velocity or acceleration.
Yeah, this one, let me see if it's really as similar as I'm thinking. The integrals and that change theorem. No, it does seem like this is about what I was thinking on for that one. But I think for a typical problem like this, you probably also have something given for the displacement S of 0. So this is my best guess of a problem kind of like that. Let me know if you've got a better one though. I know what you mean. I'm looking at old material myself right now and think I'm already judging what I wrote. So
Like this, that.
yeah, I was told by a math teacher once that good notes means you're able to put the notes away for a couple years, come back and actually read it and know what's going on. I'm not sure if I know how to do that still.
Like these are my notes for, finding the, maximum, volume,
Mhm.
yeah, the maximized volume of like a shape.
Yeah, that was the optimization section.
Like, I can understand that, but then like my work on like little things is just all over the place.
Yeah. That's, I mean, when you're learning something, there's a lot of extra noise going on in your head. It's hard to organize as you're learning. But did you want to give this one a try?
What is this one saying exactly? Is that, velocity at 0 seconds is equal to -4?
Yeah, so we have an acceleration, 2t plus 3 meters per second. Velocity at -4 means -4 meters per second. And displacement at 5 means it's displaced at 5 meters at the start of this experiment.
Okay, I think this is along the same lines. But I think you were literally only given, the velocity of something was -16 meters per second, and then it gave you one other thing to look at. I think it was like the original displacement or something. It only gave you two variables, and I was like, hey. So,
Gotcha. This might be slightly different than that one. Because on this one, all we're really doing is finding antiderivatives as we go.
Yeah, yeah.
So on this one, I'd start by, for velocity, v of t would be t squared plus 3t plus a constant. The derivative of all that would get us back to acceleration. And then we would use that initial condition right there. V of 0 is -4. To plug 0 in for your t variables, so 0 plus c equals -4. And that gives us back to velocity at time t, t squared plus 3t minus 4. So we did the absolute derivative, plugged it in the constant. And then here, all I did is plug in 0 for t to solve for c in that way. Does that make sense, getting that velocity function down? Awesome. Then we just do it all over again now. We want displacement. So that's just where it's displaced from a starting position at a given time. For reasons I still don't understand, that's s at t. Then just more antiderivatives. This would be a third t cubed plus 3/2 t squared from this one minus 4t plus a new constant. I'll call this one d, so I'm not confused with the prior one, c. But if you plug in 0 and solve, just like we did over here, we'd find that d is 5 meters on this one. So let's just write it in to save some writing. That would be the displacement of the particle at any given time.
Because like these ones I understand, but this one is so complicated. It was a very particular word problem.
It sounds like what she gave you was a situation where information was missing just right, that you had to reverse engineer what that missing information was.
That's how it was. Like it was one of them that I struggled with that I can remember that wasn't exactly like this final one.
Mhm.
It was like one of my very last exams before my final exam was where it was like a lady was standing on a building
Yeah,
and she had to throw something off and you were given the velocity of it, but you assume that the height. I was really confused on where, if the height was from where she was standing or the ground that it hit.
yeah, I see what you
And
mean.
it was just.
Or how high her hand was when she let go of the object.
Yeah, it's like I have,
Yeah,
I don't, I'm not gonna find this one. This one was like so particular that it drove me nuts. I remember going home and trying to figure out this problem on the internet, and I was just like, throwing a loophole forever.
yeah.
Or I would have just.
Because this is like chapter 5 problem, it'd be before you start looking at Riemann sums and all that kind of stuff.
All the features that well organized, any of them.
Glad to hear that. I try to put this organization in because I honestly don't know how I'd survive without it. It's for me to get through it.
And you're actually very, very thorough.
That's more has to do with, I've done this for a while. I've learned what doesn't work by trial and error. My first classes were not great. So I had to thank those students for sticking through it, I guess. Well, I gotta start packing up and get going, but what you class next time, I'd be really happy to take a look at it with you after class. Or book before class or whichever makes the most sense.
I really remember that it started with -16 meters per second.
That sounds like it had, yeah, they were using the acceleration due to gravity in that problem was the only thing they were giving you. Oh, but then there's also initial velocity. And also, you probably did you know the distance or was that an unknown as well?
It was so oddly where I could solve most of the variables, but there was one last variable that I could not solve.
Yeah,
So, because he would teach us how to do it based off like normal three-term polynomial, you'd start with just the one, anti-derive it to two terms.